Welcome everyone to well-behaved native implemented functions for Elixir. I think this is a tough time slot because I'm competing with, right after lunch between a nap or coming here. You get to do both by coming here, so, So anyone who wants to follow along, there's a repository up at GitHub at potatosalad/ElixirConf 2017. Has all the source for everything in this presentation, as well as the slides from this if you want to follow along. And there's also links for a discussion thread if you have any questions. Okay. So my name is Andrew Bennett. I'm pretty sure they named this room after me with my initials, but my GitHub username is Potato Salad, and someone beat me to it on Twitter, so I'm Potato Salad X on Twitter. And I like to describe myself as a husband, father, and programming enthusiast. These are my two girls. They're 4 and 2. My wife owns a photography business, so I'm really lucky I get photos like this pretty often. I'm from Georgia, but I live in Idaho, and we made a family trip out of driving out here. It's been fun. And I work for Vista Insurance Producers. I've been working in the insurance industry for a few years now, and we are a insurance industry technology company for agencies and agents and carriers to be able to deal with their data and help with productivity. I need to warn everyone before I go much farther that this talk has a lot of C in it. It probably has more C in it than Elixir. You might even say there's some heavy C ahead. So you've been warned. I have an additional warning about those of you who maybe haven't written NIFs before or are considering it. NIFs were introduced in about 2009 and are still kind of experimental in a way, and they can be dangerous. I think you may have heard that they can be dangerous. And I did kind of a test about a month ago, trying out the other interoperability techniques that are out there for the Erlang VM, which are much safer, like a node, using Java or C or whatever you want, or a port where it's just on the process, a process on the same machine. So there are other techniques you can use for interoperability with a different language that are safer than a NIF. However, if you have low latency requirements, a NIF is the way to go. But to summarize, what I'm trying to say here is don't write a NIF unless you have to. The subject of this talk actually comes from the ElNIF documentation itself, where it states that a well-behaving native function is returned to its caller within 1 millisecond. And I wanted to kind of test this out and find out, the limits and what happens to the Erlang VM if you obey or disobey this. And I went and looked for what other people had kind of done already. And some of the engineers at Basho a few years ago put together a test where they blocked schedulers using this kind of spin function that would keep the CPU busy for a certain number of ticks. And so this is essentially what their test did. I expanded on it a little bit to, instead of accepting ticks, to accept a certain number of microseconds that it would block for. And it does this so it keeps the CPU busy for that time, microseconds. It does this by getting the start time, stop time is the start time, plus the given microseconds, and then it just loops and spins until that time is passed. So it should sleep, or busy wait, or however you want to call it, for at least that amount of microseconds. So that's what that does. So on the Elixir side of things, we have this function that actually calls our NIF, and then I have a certain number of processes spawned up based on the number of normal schedulers that your machine has. So if your machine has 8, then if you have a 1 multiplier, then 8 processes are spawned, each of which, let's say the microseconds you enter in are 1 millisecond. So you'll have 8 processes spawned, each of which is going to wait for 1 millisecond. So if you have 10 multiplier, then it's 80, and so on. So I'm going to show you a series of scheduler utilization graphs that are recorded as a result of running this function with different arguments. So in this graph, I ran that test function I just kind of showed you with the sleep time set to 1 millisecond as kind of recommended in the documentation. And so it's kind of set up where you have a 1 multiplier, then a 10, then a 100, then a 1,000, and then 10,000. And So the last test, the 10,000 multiplier, 80,000 processes respond, and all of the normal schedulers reached 100% utilization, but I actually couldn't get anything out of the VM during that period of time. So I have that area marked as an error because it was unresponsive. You can't get anything out of the VM during that period. To give you an idea of what I mean by unresponsive, you have the terminal up with the shell up, and you press enter or enter anything, it's not going to respond to anything other than a signal sent to it. So if you're trying to kill the process, it's not going to respond to anything until that time has passed. So it's pretty severe. So this is just at 1 millisecond, which is what the documentation actually says it should be less than. So the story gets even worse at 10 milliseconds. And the interesting thing to me here is that the time for the test to run actually started to take more and more time as the so like even though in the first test, I spawned, anyway, it was just, you'll see in the next test why it's even more interesting. So the first test took 1 minute. This test took about 3. This test, I didn't go any farther than this. This is a 100 millisecond test. It took about 20 minutes on my machine. And for the majority of that time, there was nothing you could do with the VM. It was completely locked up. So now these graphs are great, but I wanted a different way to be able to visually represent what's happening to the VM. And this is what I came up with. I think it's pretty accurate. It's unable to do anything else as it's drowning. So the purpose of my talk today is to demonstrate some of the techniques you can use when writing your NIFs so that they're well behaved and cooperative with the Erlang VM. And so this graph is interesting because it's the same test that I just showed you that took 20 minutes and that was blocked for the majority of that time. This test took about 1 minute, and the VM remained responsive the entire time. I also wanted to represent this visually, and this is what I came up with. Isn't that relaxing? It's nice. And that's how you want your C code to behave. And talking about C code, this also relates to any other native language that you want to use, Rust or Haskell or anything else that you want to, or C++, anything that you want to be able to integrate in that way at the NIF level. So these techniques are kind of universal. And so the causes of long-running NIFs, or long-running NIFs are what you want to avoid, and their causes can be varied. And, I mean, the most obvious one is probably CPU blocking or I/O blocking. I/O blocking is very hard to predict, and especially in production or based on real. Eric Hinton and I did some experiments a while ago, and it's hard to get consistent results, especially when you're trying to use a NIF with I/O. And the other big thing that has bitten me in the past is variable input and output. So if your NIF accepts a non-fixed size binary list, map, or tuple, or it outputs anything like that, there's a potential, let's say you're testing out in development and it works great, it's fast, it's less than 1 millisecond, you're fine. But what happens if you feed it, a megabyte? Or what happens if you feed it a gigabyte? How does it behave? It can completely destabilize, the VM in production. And the solutions mentioned in the documentation that we're going to talk about today are dirty NIFs, yielding NIFs. I like to call them time slice NIFs, and you'll see why in a minute, and yielding dirty NIFs. And there's a fourth one mentioned in the documentation that we're not going to talk about too much today, threaded NIFs. If you need a threaded NIF, you'll know when you need it, and we're not going to go into the details today. So a dirty NIF is a NIF that cannot be split and cannot execute in a millisecond or less. And so in the code that I showed you with the spin sleep function that blocks, a dirty NIF is as simple as just telling it to run on a different scheduler other than one of our normal schedulers that runs all of the rest of our Elixir code. And so a good candidate for this is something that's completely blocking, that you can't break up into parts. Like in the crypto library, generating an RSA key is something that takes a long time and you can't really break it up into chunks. So that's a good candidate for a dirty NIF, or a third-party library that maybe you're using that you have no control over what it's doing as soon as you call out to it. Dirty NIFs are probably the easiest thing you can do to implement. This first example is kind of how we declare our C function and make it exportable to on the Elixir side of things. That's a normal one. And then the dirty one is just you add an extra flag at the end that tells it whether you want it to be CPU bound or IO bound. And then the scheduler will actually execute it on that dirty scheduler. So these are the results of the same tests at 1 millisecond this time. And you can see at the bottom, so the top part on the blue is the normal schedulers, and the bottom part is the dirty schedulers. And so you can see how instead of causing the VM to lock up, it's instead allowing everything to run on the dirty schedulers and allowing the normal schedulers to do other things. This is the same test at 10 milliseconds, and the important thing here is that it still took 3 minutes, just like our normal blocking NIF. And if we go up to 100 milliseconds, this test still took 20 minutes to run. So the amount of time taken here is the same as a normal or blocking NIF. And the thing to remember here is that a dirty NIF does not mean a faster NIF. It just means that it's not blocking the normal schedulers. That's all it is. But they can still block themselves. They can still block themselves, which is what's happening here. The next solution is a yielding NIF, or a time slice NIF. And the documentation mentions that this approach is always preferred over the other alternatives. And to understand this, we're going to deep dive for a second into how the beam does scheduling. Or the beam is also known as the Erlang VM. And many of you may not know this, but the beam actually stands for Brain Electrical Activity Mapping. And you can actually order a beam cap out here from Erlang Solutions booth. And I ordered mine off Amazon. And it's changed the way that I do my work. Here's two coworkers pair programming. And one of them is using the deprecated keyboard method, which is just not nearly as good. So actually, BEAM stands for Bogdan Bjorn's Erlang Abstract Machine, which is not nearly as fun. But so inside the beam, we're just going to talk about one scheduler. So if your machine has multiple schedulers, we're going to talk about one normal scheduler and what its responsibilities and roles are. So the scheduler is responsible for the soft real-time guarantees of the system. And so, so there's hard real-time, which means that if a process overruns the time that it's kind of given to run, the whole system is considered to have failed. So an example of that is like a fighter pilot, like a fighter jet. If I press eject, I want that signal handled relatively quickly, preferably at the highest priority level. And the system shouldn't delay a response because it's decided to go do a system update instead. The behavior of the system is called hard real-time because it's a life and death situation. And the way that the system is actually set up, it's hard real-time at the hardware level. By comparison, mentioned here that the Erlang VM, or Beam, is soft real-time. So a good example of that is like a phone. And so when I touch my screen to scroll, I expect it to be responsive to my touch in real time, and I should. However, if there is a delay for whatever reason, it's usually not going to cause me to be in a life or death situation. And so this kind of system is called a soft real-time situation. So its goal is to be as real-time as possible, but if it's not, it's not the end of the world. And it's able to guarantee these two things because of the two scheduler types that it's built on top of. The first is a preemptive scheduler, or called preemptive scheduling, where each process is given a time slice to run within. And so this is basically very similar to, like a hard real-time is very similar to this too. And once that time slice is up, the scheduler preempts or interrupts that process against its own will. So it has no say in whether or where it gets interrupted at necessarily. And so in this example, we see processes 1 through 4, and process 1 and 2 get to run just fine. Process 3 gets about halfway through, and process 4 needs to run at a higher priority level, and so process 3 gets interrupted or preempted, and then afterwards it's able to resume again. So when you write a regular Elixir code, this is how the scheduler schedules everything. This is how the code actually runs, and it's designed to work. The other type is, or the second type is cooperative scheduling. And so each task, so every time the scheduler goes to run a task, it gives control to that task. And unless that task yields or returns control back to the scheduler, the control stays with that task. And so a task can abuse that power. I showed here that task 1 outruns its time slice time. And then task 2 yields correctly, yields at good times. And task 3 yields in the middle, and task 4 is able to run at a higher priority level. And so it's very dependent on on the processes or tasks being cooperative. And so these two types of schedulers are related to the beam because one can describe the scheduling in beam as preemptive scheduling on top of cooperative scheduling. Or another way of putting this is that your Elixir functions are preemptive and C functions are cooperative, hopefully. So but let's take a look at some actual code and how the scheduler executes it differently. As mentioned, Elixir functions are preemptive and can be interrupted or suspended at almost any point in time. And I say almost because so a process can only be suspended at certain points of execution, such as at a receive or a function call. And so the scheduler calculates how long a process is able to run by giving it a time slice. And I say time slice, but it's kind of a misnomer because it doesn't use a clock. The beam does not use a clock necessarily for its time slices. It uses what's called reductions. And these help it estimate time. So when a process is scheduled, it's given, the current number is 4,000, in the past it's been 2,000, reductions to run. And so as soon as that number of reductions reaches 0, it's out of time, its time slice is done, and something else gets scheduled. So, and what is a reduction, or when does it get decremented? And it's not completely defined what a reduction is, but at least each function call should be counted as a reduction. And so let's test this with some real code. I put intermediate advanced on this talk, but the code I'm about to show you is very, very advanced, so bear with me. I think the hotel provides trauma counseling if anyone needs it. So this is our function that we're going to use. And so this is kind of how we measure the number of reductions that are happening as a result of calling to this echo function. And we start off by counting how many reductions this process has currently, making our call, and then counting them afterwards. And then we can kind of diff the two. And we get about 400 instead of 1, which I thought was interesting. Looking more closely into it, there's some noise that's happening here as a result of, because actually calling Erlang.processCall is a BIF, a built-in function, and we're getting too much feedback. And so in order to remove that noise, we need to do recursion. And so this is our recursive function that I've called collect. It just accepts a reference and a number, and then it receives on that reference n number of times. So if I give it a reference and then 1,000, I'll get back 1,000 replies. And as a side note, look really quickly at all the places that this is able to suspend at. Whoever calls collect, if it's at 0 reductions, it can suspend at that point. It can suspend on the receive, and it can suspend on its own recursive call to itself. And so there's at least 3 preemption points in this simple function right here that it could be paused or suspended at as it's executing. And so here's the test that I kind of set up. I spawned 1,000 processes, each of which are going to send back the number 1 to its parent using the reference that I created. And then we're just going to count the reductions before and after on the collect function. And we're going to diff the results at the end. And here we get about 1,400 instead of 1,000, even though collect was called about 1,000 times. But if you remember from the first example, we got about 400, which I'm counting as noise. And if we remove the noise, we get about 1,000, which matches up with how many times our count function or our collect function was called. So that definition does seem to be about right, that a reduction is roughly 1 function call, which is great. This is how it works on the Elixir side of things. But let's take a look at what happens when you call a C function. As mentioned in the Beam book, which is a great resource, by the way, if anyone's wanting to learn more about this. There's a risk that a function implemented in C may take more clock cycles per reduction than a normal Erlang or Elixir function. And this is due, I wanted to go see exactly how the Beam actually calls a NIF. And in the code, it's literally just dereferencing the function pointer to the C function and just passing it the arguments in the environment. And that's it. It doesn't do anything else to try to regain control or anything. Control has been completely passed to your C function at this point. And this blocks the entire thread, the entire scheduler thread, until you return or you yield. And so let's take a look at what happens with the reductions when we do this. So this is the C version of that really advanced function from before, where it just, you pass it a term and it echoes that back to you. So this is a very similar setup to our first test in Elixir. The only difference is that we're calling our NIF echo instead here. And the difference is also is that the number of reductions we count are about 200 instead of 400. And so again, there's some noise happening here. And let's try to see what we can do to reduce it. Or actually, let's see what happens first if we have our C function do a little bit more work. So I modified it so that it would have the spin sleep function spin for about 1 second. And that's a lot of time for the CPU to be doing work. And but if we run our same test again, we only get back about 200 reductions, the same as if it had done no extra work. The scheduler has no way of knowing that your function has done more work than just simply returning immediately, which is bad because, remember, the scheduler uses reductions as its basis of time. And so it throws off its sense of time and can lead to, I think the documentation uses the words strange behaviors, which is true. But there are ways that we can keep the scheduler informed. And with enif consume time slice is the main way that we have. And if you feel like I'm taking a long time explaining, getting to this point, it is very time consuming. Anyway, so fire echo function again and call consume time slice. And so the way that it works is you pass it the environment and then a percentage. So you can say, like, of this time slice, I am 50% done. And so, but we're just going to give it 100% and see what happens and measure the reductions before and after. And we get back about 4,200 reductions. And so if you remember from earlier, the process is given 4,000 reductions at the start of its execution. And we had about 200 reductions in noise from our simple echo function. And so if we remove the noise, we get back the number of reductions that it was given at the beginning of its execution. So giving it 100%, they're saying, hey, I've used 100% this time slice means that it will use up all of the rest of the reductions that has been given. This is how you have to communicate in your NIF to allow it to, so that it doesn't throw off its sense of time. So I wanted to go into a little bit more depth about a technique that kind of Steve Vinoski came up with that kind of that he uses to kind of automatically adjust the number of the amount of work that we're going to do per slice. And but I thought it was more important to kind of explain why that it throws off the scheduler's sense of time. And so I'm just going to kind of breeze through this part. You don't have to understand everything. But we're basically modifying our spin sleep function. I showed you how to turn it into a dirty NIF, and then we're going to be turning it into a yielding NIF. So we're modifying our spin sleep function from earlier and detecting if the microseconds are greater than 1,000, which is 1 millisecond. If it's greater than that, we're going to yield immediately and use a different function. We're going to schedule ourselves for future execution to run a different function that uses time slices. And we pass here just an estimated guess of 1 million. So that's how many ticks we're going to do per slice starting out. And then we're going to call consume time slice and find out, hey, do we have more time to do more work, or are we completely done and we have to yield immediately? So that's kind of how that is designed to work. This is the beginning of our time slice version of spin sleep, where we're pulling start, stop, and max per slice back out. And then this loop basically spins using max per slice, calls consume time slice kind of there at the bottom, based on what percentage of 1 millisecond is completed. And don't worry about this too much. If you happen to be implementing this in the future, reference Steve's work or this, and you'll find it useful then. And then if consume time slice can either be true or false. If it's false, you have more time to do more work. If it's true, you need to yield immediately. And so this is what happens. This is the code related to yielding immediately. And here I'm just adjusting the max per slice based on how many iterations we were able to get through. So if I gave it 1 million and I was actually able to get 3 million ticks done, then that can be my new max per slice the next time I'm scheduled. So that's kind of what's happening there. And these are the results. And so this is our 1 millisecond test. There's very little scheduler utilization. Even with 80,000 processes spawned, at this you see a little bit of a blue spike there, but in each of those 80,000 processes are all blocking for 1 millisecond. This is 10 milliseconds, and you can't even really tell the difference between the two graphs. You do start to see a little bit of a spike at 100 milliseconds, so I decided to push this a little bit further beyond 100 milliseconds to find out what would happen. And at 1 millisecond, we are starting to see some slowdown, some degradation that's happening as it reaches 100% utilization. And at 10 seconds, errors start happening. And so one of the reasons that this is happening, I looked into it a little bit closer, is what's called thread progress. And I'm not going into much detail today about it, but Lucas Larson does a really good talk about it a few years ago that I recommend watching. But I wanted to see if there's a way to solve even this problem. And so I come up with, I'm calling them yielding dirty nifs, and they're not actually mentioned in the documentation. But they're very simple. Well, after you've gotten to this time slice point, they're very simple. So after you've gotten your time slice code working, all you have to do is pass this flag when you're scheduling your NIF that tells it to run either on the CPU bound or the IO bound scheduler. And so that's how that works. The results of that are that most of the work is actually being done. You see the green down there on the dirty schedulers. And the interesting thing is less than 100 milliseconds, it's actually worse performance with a yielding dirty NIF than with a regular yielding NIF. And so 10 milliseconds, same thing, 100 milliseconds. And then at 1 second, you'll notice that the normal schedulers start to be less utilized as the dirty schedulers are at 100%. And I did the same test at 10 seconds. So the normal schedulers actually dropped to 0 utilization. And the same thing at 100 seconds. I was actually able to do that. And so during this entire period of time, the VM remained responsive, which is pretty cool. And so that was a lot of graphs and information to digest. So I thought we could take a moment to get some eye bleach and enjoy this kitten cuddling with a duckling. Or this puppy who doesn't even know what a NIF is. So, so jumping back into the results. I kind of put this together that kind of shows the summary of you can see the delay that's starting to happen. This is the measured delay as the time that each NIF was taking, was introducing to the VM. And so whenever it was read, we were getting errors back from the VM. And so based on these just alone, that you can see how time slice NIFs are the way to go by far. So my recommendations based on that information are actually, if your NIF is provable at less than, if it is definitely less than 1 millisecond. Remember what I mentioned about variable input or output. Make sure that you test against that too. If it's less than 1 millisecond, you can get away with a normal NIF. If it is greater than 1 millisecond or less than 100 milliseconds, a yielding NIF is the way to go. And greater than that, a yielding dirty is the best way to solve that. And so everything that we did so far was based on an idle VM, an idle beam. And I wanted to actually test a closer to real world thing. And so I decided to test Cowboy 2 with HTTP 2. And so this is the baseline test I did. We're getting about 40,000 requests per second. This is running for about 5 minutes. But instead of punishing it with 16 slides, slides with 16 graphs on them, I decided to shove them all into one slide. And so, actually, at Gary's talk yesterday, I realized I can get off the stage, so I'm going to do that point. So this right here is our normal NIF running at 1 millisecond, 10 milliseconds, and 100 milliseconds. And we can see even at 1 millisecond, it drops down to about 100 requests per second instead of 40, down from 40,000 on average. And I kind of tried to highlight yellow and green and red based on which ones were good, kind of good and bad. So you can kind of see how there's kind of this band that kind of goes diagonally right here of green, where the yielding is good up to about 100 milliseconds. Then after that point, yielding dirty are actually better. Dirty NIFs are still good. Like if that's all you can do, if you cannot prevent something from blocking if you're using a third-party library, they're fine. But if you can break up your work, a time slice NIF is significantly better. And there are some examples of NIFs actually in OTP. In crypto, it's probably the biggest example. There's lots of time slice examples in there. More so I started playing around with time slice NIFs probably 2 years ago. Well, I can't remember when they came out, so I may be lying. Anyway, a while ago, and slowly, like the crypto has gotten more and more time slice functionality built into it. And there's one dirty example in there, the one I mentioned earlier about the RSA key generation. And examples in the built-in function side of things. So NIFs and BIFs are similar but not in a lot of ways. But you can learn a lot from reading some of the BIFs that are in OTP about what you should be doing with your on the NIF side of things. And there's examples related to binary match, matches, and split. So those are especially fun. I submitted a pull request to OTP about in May, and it's just barely starting to get approved now. So those are especially fun because they accept variable input and variable output, especially on split. And so you had to use time slices as it was doing the first part, and then time slices as it was doing the output part too. And so that may be helpful to someone. Some of the new features to NIFs in OTP 20 are that we have magic references now instead of magic binaries, which are very cool. And what's interesting is that there are more and more features that kind of have in the past existed in port drivers that are slowly being kind of converted over by the OTP team to the NIF world. Examples of that are like where's PID, where you can look up a PID, like a process based on its name, like it's like using an atom. You can monitor a process, and so if that process dies, it will actually call C code the moment that process dies. And then really cool is enif select, which allows you to do an event loop on the NIF side of things. And so based on enif select, there's some really fun things done. It's kind of examples by the OTP team, by Sverker Eriksson, hopefully I'm pronouncing that right. He has a potential TCP replacement, which currently is written as a port driver, but it might be able to be replaced as a NIF one day, especially if they're able to figure if we're able to figure out some of the IOQ stuff, which is only in port drivers right now. Same thing with the TTY replacement. He kind of has an example of that, which is pretty cool. Also on the TCP thing, the initial benchmarks that I ran on it is faster than the port driver one, and so it could be a lot of fun if we can get that working. And then just for fun, a few months ago I played around with a threaded NIF using libh2o just to see if I could get it to work as a plug backend. And it's not usable. Nobody, like if you get it to compile, you should get a medal. And but I was able to get it up and running enough to be able to do some tests with it. And so these tests here on the bottom are Cowboy 2, which is really fast. So this is not to say that Cowboy 2 is not fast. It was just interesting to me how there's a lot of fun things that we're going to be able to do with NIFs in the future. A lot of performance to be had. And that's it. There's the repository you can go to. There's a discussion link if you have any questions. And thanks.
Okay, we have time for questions. Oh.
Hi. Are maps from list to list BIFs or the time-sliced versions of that anywhere on your radar? Because I know all of Phoenix would benefit immensely if we got time-sliced BIFs for maps to list from list.
I saw some discussion about it a while ago. I need to go look that up again, actually. I know one of the priorities about a year ago was to get term to binary and binary to term converted over as a time slice so that they weren't blocking anymore. But I'll have to look that up. That's a good question.
Hi, you mentioned like the dirty nifs. You're basically the time stays constant. It doesn't get faster, but it kind of allows the VM to be responsive, moves it off to a different scheduler. Is there any other side effect for dirty nifs to push that work into the dirty scheduler? Do you see any other maybe performance issues with that, or?
Yes, I should have mentioned that on the graph. If your nifs are fairly fast, it can actually be slower because of the context switch involved to send it over to the other thread instead of just allowing it to run on the same thread. And so, yeah, that's kind of what I've noticed. And there's also issues with, that's the biggest issue, but yeah, that I've noticed.
On the when you have a dirty NIF, it creates a dirty scheduler just for that NIF. If you have two NIFs, both dirty, does it create two dirty schedulers? And if so, like, do you have to be concerned about creating too many of them?
So that's kind of what you had to do in the past before dirty NIFs. There was actually a thing also from the Bash engineers called async NIF, which is similar to what you were describing. Dirty NIFs, however, are and I think they're default in OTP 20. It spawns up as many dirty NIFs as there are by default as there are as normal. Sorry, it spawns up as many dirty schedulers as there are normal schedulers by default, and so you just have 8. If you have 8 normal schedulers, you have 8.
So if one NIF's blocking the dirty schedulers, and another NIF comes along, it'll block the second dirty scheduler and so on. And then you could potentially block all the dirty schedulers. That's that. Okay.
And so one of the problems that I've kind of I mean, I hope this doesn't happen, but if let's say everyone out here goes and writes their own library with a NIF, and then we all use dirty NIFs as our solution, we'll be blocking each other if 2 of those libraries are used in the same application too much.
Got it.
Anyone else? Do you have a question here? Or no? Okay. Thank you.
Thanks.